Good afternoon, everyone. Thank you for joining us on our webinar. Today, we are glad to have Dr. Christian Freck, our customer support engineer based in Germany, with us. Christian has obtained his PhD at University of Dresden with a research topic in situ electrochemical scanning probe microscopy of the deposition of conducting polymers. After he did a postdoc at the Institute of Polymer Research, Dresden, on AFM on polymer. With experience in scanning probe microscopy for more than 25 years, Christian has been working as customer support engineer at Bruker for more than 13 years. So for today's webinar, we'll focus on AFM applications in fluid imaging. The topics will cover the reason why we use fluid imaging, required hardware, different techniques for AFM fluid imaging, and etc. At the end, we'll have 15 minutes for a Q&A session. So, all right, let's pass the wheel to Christian, and Christian, please go ahead.
Okay, great. Thank you, Jan. So hopefully, can you see my screen? Now you should see it. Let me know if not. So I will just start about the fluid imaging. Parts of the presentation, a big part is made by my colleague from the US, Yingming Hua. And so I put my name on there because I also did some transparencies there. So why are we doing fluid imaging? So basically, in fluid, we have the advantage that it reduces adhesion forces, meaning meniscus forces, because on every surface we have for our Bruker AFMs, there's a small water layer. For very small scanners, for the multimode, for instance, like the A scanner, which is only capable of scanning 0.7 micron in X and Y and about 500 nanometers in Z, you cannot really get rid of the water layer. Therefore, for the very small scanners, it's actually crucial to reduce these adhesion forces. A larger scale scanner can overcome that, but still you have always a water layer. It also allows measurements in the native environment for some polymers and for sure the majority of the biological samples like cells. Again, from my point of view, so from my profession, it allows you the in situ study of sample surface during the physical or chemical processes, like a chemical reaction on the surface, like in my case, way back, electrochemical deposition of polymers on the surface, crystallization processes, dissolution processes, or adsorption processes can be imagined. When you look at the icon system we have, here's a look at the hardware which is required, which is the so-called liquid cell holder, where you have a small clip for releasing a spring, and you have the typical 4 mounting sockets here. If you turn the holder around, you see that you have a cantilever mounting groove here where you put the cantilever in. You have the spring clip to hold it down as on the air holder, but a slightly different technique here. And you have a glass window which allows you the laser to get in and out. The whole system is usually made out of KLF, so it is proof versus a lot of chemicals, which helps you also for experiments in non-aqueous solutions. However, you have to refer or ask us if your organic solvent is capable of functioning with a cell. In addition to the cell itself, or the holder, actually, there is a splash guard which is covering the scanner to allow the system or to shield off any liquid which might otherwise get into the scanner and might damage it. You can see it here on when it's turned around again, how it's looking from the other side. Here's
Sorry?
also yes.
Sorry to interrupt. Your slide is not changing. We are still looking at the first page.
Okay, is it working now?
Yeah.
Okay, sorry. Okay. Good. So good. So again, hardware. Again, you have the holder here, where you have the clip release button for the spring, which holds down the cantilever. You have the typical mounting sockets here. You have a glass window where the laser goes in and out. The whole system is made out of KLF, so the holder, most of it is made out of KLF to be chemical resistant in fluids. Again, ask if there are questions about the solvents you can use. There's in the help function of the multimode nanoscope version 9 and onwards, there's an online help where you also can look for the fluid cell compatibility towards other chemicals. Then you have the Viton splash guard. Now you can see here, which saves the protects the scanner from being contaminated or getting into contact with water. And down here in the lower right side, you can see the standard holder for the cantilever stand, where you can basically exchange the probes. For instance, in the front right part, you can see the standard air holder, which cannot be used for the fluid cell, but the fluid cell is the one with the small wire on top of it, which basically then presses down the clip release button when you put it on, and then you can easily exchange the cantilevers. So there are some precautions you have to take care of. So one is you cannot, when working with the icon, you cannot use the alignment station for laser alignment when you're working in with the fluid holder, because the fluid holder is much thicker than the air holder, and therefore the preset Z position on the alignment station will be wrong, and the holder would crash into the alignment station. Therefore, do not do that. There's a good way to do the alignment, laser alignment, just with a sheet of paper underneath the scanner, that you see the reflection there, and then you can move it over like on older systems or as on the multimode. Again, it's very important to do not spill any water into the scanner, because this destroys the piezo ceramics inside. Therefore, if you feel more comfortable, use the splash guard. It is recommended. If you're using software version Nanoscope 8 something, so 8.0, 8.1 or 8.15, or up to software version Nanoscope 9.1, please reduce the closed loop sensor gain, eye gain, from 12, which is default, to 8. The reason for that is basically the sensors are reacting to changes or where the scanners move non-linear, and the thing is, the holder is heavier than the standard holder, and therefore the system reacts slower and with a slower response. So even when the system is trying to engage, it checks the scanner movement before that, and technically more or less shakes the scanner to check for the movement. And since it's heavier, it gives a different response, and you will have an instant crash protection turning on if you do not reduce the closed loop sensor eye gains to 8. You can get away, maybe it depends on the system, with something the eye gain set to 10, but it has to be mostly lower than 12 for sure. In later versions, like Nanoscope version 9.3, release version 1, uses a different eye gain setting, so it is set to 2.4 by default, so you have to reduce it to 1.6. With the later versions than that, Nanoscope version 9.3 R2 or 9.4, the gain is digital and therefore doesn't need to be adjusted, as far as I know up to now. So there's also one thing you have to check for, which is a false reflection of the fluid cell itself, where the laser beam coming from the top is reflected by the slightly tilted glass window. and therefore gives also a strong reflection in the photodiode. And you have to be sure that to make sure that you align the laser from the cantilever into the photodiode. You can basically do a small change of your laser position, and this will have a dramatic change of your thumb signal. Meaning, if you turn the back screw of on the cantilever on the icon scanner clockwise or counterclockwise in small circles, then you will see that if you were on the cantilever, the signal drops instantly. If it reflects on the glass, it stays there much longer. For the multi-mode, the hardware looks a bit different. You have here the liquid cell, which is a bit larger. The standard liquid cell has an inlet and an outlet. It can be sealed off with an O-ring, and you can connect the fittings here with the lure fittings directly to get your fluid in or out. When you work with a multi-mode, you have to take care of, again, when you're imaging in fluids, you have to be careful against spillage. Same goes there, because here the scanner is at the underneath the fluid. The fluid must not be spilled on or around the components containing the electronic parts. Of course, you have to avoid spilling all corrosive fluids on exposed surfaces, of course, otherwise you might damage your scanner or your surfaces. You should immediately clean and dry any leakages or spills you have very carefully. You have to be careful also when using the O-ring. For instance, if you put on the O-ring, be sure, and if you fill in the liquid, be sure that it's really sealed tight. Otherwise, you may have some water damaging your scanners over time. By the way, for the multi-mode, you have scanners which are liquid resistant, and when they are shipped to you, and when you buy them, they have a 3-year warranty against leakages that your droplet would go in. They have a rubber sealing. The standard scanners do not have that. In any case, I would also recommend using something like parafilm to shield off the top surface as well. Something about Snell's law, just about more or less that the laser light, or light in general, is reflected differently in water than in air. Overall, this has 2 effects here. The laser path changes when it enters from air to water with an angle, and the objects in the water appear shallower than they really are, which can be also observed, of course, in nature, but for sure on the icon system and also on the multi-mode. This means, so you have the laser path changes after water is applied on the cantilever. And overall, what is good practice for measuring in liquids, and this will be repeated a couple of times, a drop of water needs to be put on the cantilever to make the engage in fluid easier. Has 2 reasons. One is then it's already pre-rinsed, so if you do not need to bring the cantilever from air directly in the liquid, where it might just bend a bit on the water surface, and then you might have a false engage, and then you have to start again and again. This is one thing, and the other is also to try to reduce air bubbles, which might would be generated in this lamellar way of the V-shaped cantilevers, for instance. Because of the refraction index change from air to water, the laser path will change after you applied water on the cantilever. For the icon fluid cell, after you have applied a droplet of water, the laser spot will shift about 30 micrometer closer to the cantilever chip base, so closer to the substrate. So, and you can see that there's basically in air, when everything is aligned and the laser is in the middle, it will shift in the photodiode because it's shifted because of Snell's law. Just keep that in mind. So how to realign the laser after adding the fluid is in fluid, we need to align the laser blindly. So now you cannot use for sure not the alignment station, and even if you have a reflective surface, it's hard to see the laser somewhere in the water, so you move the laser to the left slightly, that it hits again a leg. Then you move the laser up or down to get the laser spot directly on the leg. Then you move it the opposite direction and maximize also the sum signal to confirm it's really hitting the other leg if it's a V-shaped cantilever. And then you move the laser in between and then towards the left that it's back at the top. You can also do this in intermittent steps, like going on one leg and then along the one leg towards the left side and middle center of the laser. This is slightly depending on you. Again, so also the objects in the water appear shallower than they really are. Because of the light change of the air-water interface, it appears closer. On the icon fluid cell, it is about, it appears that the focal point is now at about 750 micrometers, not at 1000 micrometers, which is the standard. Here's more theory to that, but in the end, again, if the sample is 1000 micrometer below the tip, in water it looks like it's only 750 micrometers. For the icon system, we have a focus auto compensation button, which you can check if you select in your experiment, for instance, contact and fluid, and you go to the setup. You will find from the setup, go to the navigate, and in the navigate you find a checkbox where it says please auto compensate for the fluid. This will automatically change the settings to the correct height that is again in focus. My colleague put here a question: what will happen if we check this function when the setup is pressed in air? Basically, you are then off by 250 micrometers. So I would usually, and this is what we, if possible, I would in general try to set up everything in air first before filling in the water, but I'm coming to that later. The objectives, again, appear shallower. This is a bit more about it. You can see the numbers. When you work in air, it's around minus 4,100 micrometers. The optics value here, the same goes for when you add the fluid, but then everything is out of focus. And it's not only that it's changing in appears shallower, but it's also the lateral position shifts slightly to the left, so it's different height here, and the whole image shifted slightly to the left. Again, these are optical effects by the system. So in general, what is the method here for the icon? Again, you would try to set up everything, the tip sample distance in air. So select your experiment as fluid, align your laser, again, not on the alignment station, but manually on the cantilever, and then go to navigate. After focusing on the cantilever, go to navigate and focus on the surface. When the surface is in focus, you're again 1000 micrometers away from the surface. You can then remove the scanner and turn it upside down and put a droplet of water, what you can see here, put a droplet of water on the cantilever, and put a droplet also of water if you're working in water on your sample. And then you put your scanner back in and tighten the screw. And now the cantilever is completely covered with water and it's floating, or it is in the liquid, completely in the liquid. The question here is, what if the sample has to be in fluid all the time? Imagine some cells, and you still want to use this method. I would usually recommend try to find a dummy setup where you're at the same height as your surface, and then focus on like petri dishes, etc., which are about the same height. So just focus on them, that you're this 1 micrometer away. Replace it with, so lift the scanner up, replace it with the original cell with the fluid filled, put my droplet of water or buffer on the cantilever, and then put it back in. So this is also helping there. So for the multi-mode, it looks slightly different. So here you have the multi-mode setup, where you from the right fitting, you can fill the fluid in. The one which is technically in the middle of the cell is more or less the overflow, where the water would come out. If you insert the water from the right-hand side and let it go into the cell, you would need to use an O-ring for the tight sealing. What I usually do there is I engage in air in standard settings, and then just instantly withdraw, because then I'm about 20 microns away from the surface, remove the head, and then I install the O-ring, and then I would fit it from the side. You always have to check for spillage there. So if you put too much, the cell itself, except for the fittings, has about 80 microliters volume, so it's not so much. So if you have to push in there more than, let's say, half a milliliter, then there's something wrong. You have to look for leakage somewhere. There's a mirror. I'm coming to that in the next image, which needs adjustment on the multi-mode. On the next slide. Overall, and the same goes actually for the icon. You should wait 5 to 10 minutes that this signal stabilizes and the system comes into equilibrium. So here you can see from the multi-mode head the mirror, which usually just reflects the laser beam, which goes from the top down on the cantilever into the mirror and then into the photodiode. And since the laser light comes straight down with the tilted cantilever, so we have to readjust the mirror. On all available heads now, there's a small lever at the back side, which you can slightly adjust to optimize your signal. So in using the multi-mode, I would set up everything in laser, spot everything in air first, engage once briefly on the surface, withdraw, then again also put a droplet of water on my cantilever on the multi-mode and a droplet of water on the substrate. If I'm not using the completely sealed system, then that should be enough. If you use the sealed system again, then you have to slowly fill in the water from the side. Also, again, when you put on the O-ring and you're just 20 microns away from the surface, everything should be fine. And be aware again and check for air bubbles, because then you cannot put a droplet of water on your cantilever if you fill it up from the side. Otherwise, the O-ring will not be tight. You can, instead of just using a syringe to fit it in, you can use the tubings here. In this case, again, you would fill the right tube with your liquid and wait till from the middle position or the left tube, the liquid would flow out, and then you can use clamps to close the connection. Then the cell is full and completely filled. Again, please there use the O-ring and check for leakage. So again, back to the icon. You should mount the probe in the fluid cell, mount the scanner and put the scanner splash shield in place. By the way, it is for AFM studies in fluid, this is very, very, very important that the fluid cell is clean. I'm talking about cleaning the cell a bit later. So at first, align please the laser and set up the tip sample separation while everything is dry, if possible. Bring the probe close to the dry sample surface. So again, for the icon, it will be 1 micron if everything is in focus. Again, align, so put the tip into focus, and then go to navigate and focus on the surface. Then remove the scanner, put a droplet of the imaginary fluid on the sample and on the cantilever. Again, why on the cantilever? It's to avoid the air bubbles, again, the lamella on the V-shaped cantilevers, and also minimizes the problems with the cantilever interaction with the top of a drop. Okay, so then you put the scanner back into place. This will produce a meniscus of fluid between sample and fluid cell. You should add more fluid if needed to form an adequate sized droplet. Since on the icon the system is not sealed or cannot be closed as on the multi-mode system, the fluid will evaporate over time. So what you could do for that is, what I usually do is put a big beaker of my fluid on the on the right-hand side of the icon, where I can put things down there that at least when I close the hood, the humidity stays constant, so that you don't have as much evaporation as when everything is open. Again, when you are working on the icon, you have to realign the laser position on the cantilever. So the laser spot will now be focused at a point behind the end of the cantilever. So you have to move, turn the upper right screw counterclockwise to move the laser again on the cantilever, and then again optimize your laser signal, sum signal, and also optimize your photodiode signal. So adjust the photodetector, and then if you're working in tapping mode, for instance, then you would tune the cantilever, and then you could engage on the surface. Here again, some photos of that. So mount the cantilever, focus on the tip and set up the laser in air, apply a droplet again and of fluid and on the cantilever, and realign the laser and refocus on the tip. Then you move this stage down until the sample is in focus, and please use the auto compensation. Then everything should be correct, and then you can engage the tip. By the way, what you can see here is also that if you're working in a Petri dish, you have to be careful that your Petri dish is not hitting the objective on the left-hand side. So just be sure that your Petri dish is moved slightly more to the right than to the left side. If you work with a Petri dish, it might happen that there's a drum effect in tapping mode, for instance. If your Petri dish isn't just sitting on the chuck, not held by vacuum or anything, then your cantilever is like a drumstick on a drum, and you will see vibrations which you cannot get rid of. There are two ways to overcome that. One is using a glass bottom Petri dish, which has a very planar bottom, and where you can use the chuck vacuum to hold it down. Or you can use, if you have a polystyrene Petri dish, for instance, you can put a small O-ring underneath it and then also hold it down with vacuum. Then this drum effect will be much less. And then this, you are on the safe side. So this is much better if you need to work again in a Petri dish. Again, these are the major settings for the icon. Set the XY sensor close to 8. I spoke about that already. Speaking of version 9.1 and earlier, or otherwise, please ask us if you say, hey, we always have an immediate engage there, or crash protection turns on. Set up the sample in water and place it on the sample chuck. Mount a probe on the holder, mount it on the scanner, put the splash shield in place, align the laser in air using the shadow method. So, this is about, when you're working directly in liquid, not fill up later. So again, don't use the alignment station. Place a droplet of water on the cantilever, and then move the laser alignment in the X direction to realign the laser. So again, right hand side screw counterclockwise. Mount the scanner and lower it until the droplet of water joins and forms a meniscus with the sample. Refocus the camera, adjust the photodetector, tune the cantilever if you're in tapping mode, and engage on the tip surface. In addition, again, wait at least 5 minutes to see if there's some drift in the cantilever or in the laser movement in the photodiode, usually due to temperature effects. What probes you can use? So here's a list of these. So for instance, we have the SNL probes, which have 4 different V-shaped cantilevers at various spring constants, depending on what you want to measure with them. They were designed originally to measure in contact mode, but also can be used, but I'm coming to that later, for Scan Assist and for one of them also for tapping mode. It has a tip radius of 2 nanometers, so it's pretty sharp. You can use the DNP probes, which have a similar spring constants, but they have a larger radius, as well as the DNPS probes, which are also more made for biological samples, where we sacrifice sharpness of the tip versus stability of the cell membrane, for instance. Similar to that, also the MSNLs with slightly different spring constants. They are rectangular and triangular. They're also the MLCTs and the MSCTs with various radiuses. Nowadays, for Scan Assist, we recommend the Scan Assist Fluid Plus, which can be, so let's speak for tapping or Scan Assist in general. The Fluid Plus has a diameter, tip radius of 2 nanometers. The Scan Assist standard fluid without the plus has one of 20. Again, can be used for biological samples, or nowadays also the FastScan C probe. You don't need to run it on a FastScan head. You can also use it on the standard Icon scanner. There are 3 primary modes which can be used in fluid. One is contact mode, which is easy to operate, but you have shear forces which might scratch delicate samples. You can use tapping mode, where you don't have the shear forces any longer, but it requires cantilever tuning to find the right frequency, which is not easy. You can only for this, because you need a cantilever which has a reasonable resonance frequency. You can work with 3 different cantilevers. One is the SNLC, the DNPC, again, same properties concerning the cantilevers, different radius, or the Scan Assist Fluid or Scan Assist Fluid Plus. In Scan Assist mode, you don't have the shear force at all. There's no need to tune the cantilever, and it's easy to operate. So if you're working on a multi-mode which is capable of Scan Assist, or an Icon system which is capable of Scan Assist in fluid is the easiest mode of the 3. For tapping mode, so you can see here multiple peaks in the cantilever tuning, and usually the standard resonance frequency is actually decreased by a factor of 4 when you're working in liquid. So, and it's also the peaks are much broader. And since this, we have multiple peaks. Usually, the cantilever auto tune will not work. What you can do is you can use fast thermal tune instead, and to determine the cantilever resonance frequency. And then you would manually offset the drive frequency close to the cantilever resonance frequency in fluids. As you can see on the right-hand side image, you would see here a huge blue peak from the tuning curve and the red dots from the thermal tune, and you would slightly offset the drive frequency slightly off from center. And this dampening, in fact, is significant, and only certain cantilevers can work well in tapping mode in fluid, like the SNLC or the DNLPC, or again the scan assist fluid probe itself. One other thing which is coming here to my mind is that here usually we have a resonance frequency of the SNLC of, I think it's either 12 or 17 kilohertz. So it's a high-pitched noise, which is not nice to hear. So either you have to work in the hood that you don't hear it, or put the thermal cover over the multimode in case of the multimode, or you should wear something to protect your ears because it's just an annoying sound. Peak force in tapping is much easier because you have a direct force control during the scanning. It can give you higher resolution topography and mechanical properties at the same time. This is the big benefit of the peak force in general. And in liquid, everything is also possible there. For you can see some, for instance, if you run it on a cell, for instance, there might be changes of your images. You might have some artifacts from the scanning in the measurement. Just be aware of that the forces will change from this point when you go up here, and even then if you're in the region where you basically, your cantilever is, your tip is basically blocked by the height of the cell here, your force behavior will look completely different. And so therefore, it's not easy. You have to look for these artifacts. The cell topography causes the force background to change when you scan in different locations. What you could do for a better image is use scan on a smaller area to minimize this change. You can use a lower frequency, for instance, 250 hertz on the catalysts. So this is usually we would have something like 1 hertz, but nowadays all systems with the latest software can go down to 250 or even 125 hertz. Or you can use a taller tip, so you have a taller radius, the taller height of the whole thing, that it's not interfering with the pyramid any longer. Have a look out for the peak force tapping sync distance to know that you're really in a good area where your feedback works well. For instance, on the left-hand side where it says incorrect, basically your blue curve is the approach curve more or less, and then you see like an overshooting of the red curve of the retract curve, and then so your feedback wouldn't work here correctly. And for that, basically, you have to press this auto config button a couple of times, that the blue and the red at least are superimposed where the feedback starts. So this means the time for the measurement, the sync distance is technically a time for the cycling of the force curves. The timing is then correct, and then your image quality will increase a lot. The parameters itself, the recommended probes for the whole thing are short cantilevers with a here Here it says it's recommended that the longer cantilever on the same side of the substrate has to be removed because it might interfere. Again, so you have just remember that you have two cantilevers neighboring each other, one short, one long. So you can remove under an optical microscope, you can remove the longer one with a scalpel, for instance, carefully, or with a tweezer. That's not interfering the measurements in fluid. Usually, up to my knowledge, I haven't seen much of a influence there, but again, so my colleague says it's better to work without it. So if you can do that as well. Other parameters again is fix the Petri dish to reduce the drum effect, low peak force tapping frequency. Again, default on a catalyst is 1 kilohertz. On the multimode and icon is 2 kilohertz. So use a lower peak force tapping frequency. Again, half a hertz, quarter of a hertz would do the trick. You should adjust the lift height to remove the background correctly. You can also scan a smaller area if possible, and increase the peak force amplitude to get higher if you have to go over high features. Here's an image of peak force tapping of calcite. In this case, was done with a multimode with an e-scanner. Probe is here, so these are more or less recommendations. Again, you can then start to see atomic lattices. One of the major points here again is working clean. Basically, this is about the AFM cantilever and the optical lever. How sensitive the cantilever is characterized by the deflection sensitivity. The unit is nanometers per volt. A short cantilever has a better deflection sensitivity, so it's proportional to 1 over the length. Overall, short and soft cantilevers are the best for the atomic resolution, and a dirty fluid cell can deteriorate the deflection sensitivity because something is bending in there. You might not see a fully good force curve with a hard wall contact, but you might have some elasticity effects in there, and then your deflection sensitivity will be off. One more thing is the same cantilever can have different deflection sensitivity on different systems, meaning your deflection sensitivity will be different between a multimode and an icon, even if you use the same cantilever, because the laser path is different or longer on the icon system than compared to the multimode. Here are the probes again. So again, the best choice would be small and soft cantilevers for working in fluids. Small cantilevers have also less hydrodynamic damping in fluids, and the recommended ones are again the SNL-C, the Scanosys Fluid Plus, or the FastScan C. So here you can, on the left-hand side, you can see in the drawing of the SNL cantilevers, and the SNL-C is the short cantilever which has the thin legs. When you have them in the Bruker package now, the SNL-10s, the A and B cantilevers are facing the Bruker logo, the C and D cantilevers are facing the opposite. A bit more about the contamination control again. So you should use tweezers to hold the liquid cell, and your tweezers should be cleaned with ethanol or IPA. And you should wash both the fluid cell and the sample with a soft toothbrush, here called a baby brush, and water, and rinse with DI water. My colleague recommends soap water, so some slight detergent inside. However, if you're working with surfactants, for instance, then I would strongly be against using any soap there. Just use IPA in the beginning, or ethanol, then water, and then rinse with DI water. Please dry it with clean nitrogen or argon, or clean compressed air, but no canned air where there's usually oil inside, which then would again contaminate your surface of your sample or your cell. And use a clean container to transport the fluid cell and the sample. Don't carry them in your hands. Recommend is also to wear gloves when you handle the parts. You shouldn't breathe on the sample or the probe holder, of course, again, contamination. You should use analytical grade pure water like MilliQ or millipore water. Regular deionized water is not clean enough, and you should use a clean or fresh pipette to add the water to the tip and to the sample. Here you can see the influence of the contamination. On the left-hand side, you see calcite in regular DI water, and on the right-hand side, you see calcite in pure water. And this is required for atomic resolution for sure. Regular DI water, even if you filter it, is not clean enough. And the soft particles from the DI water droplets from the DI water deposit on the surface, and they wouldn't even just stay there. They could also contaminate your tip, and then you would have, instead of a very sharp, atomically sharp tip, you have a particle there, which is then not allowing you, give you a good resolution. So please work clean when you're working in liquids. Again, for the special case here, in this case, measuring on calcites, set up the sample distance and laser align it in air to minimize the operation once you have fluid added. Further, to clean the sample surface, add a few drops of pure water on the sample surface, then wait for 5 minutes and then remove the water. Carefully, just by having a small tissue here with Kimwipe lint free, which is basically then sucking off the water again. With that, you can also get rid of the contaminations on the calcite surface. You would prepare the engage here with a very low peak and force set point and also very low amplitude. These are the engage parameters from microscope engage. And in addition to that, the set point also should be set to manual. Here, your Genesis auto control should be off. Your gain should be at 2 at the beginning and 0.02 volts for the set point. You can start with the peak force frequency, which is high, and then reduce it later. And you should set the engage amplitude to the same value as the scanning amplitude, and use the minimum engage set point without causing a false engage. You will see that, so just be as gentle as possible. And again, turn off the Scan Assist auto control. When you're on the surface, you would optimize your scanning parameters, again, using autoconfig to get a good overlay of approach retract curve in the force monitor, to make sure that your sync distance has a good feedback there. And then you can adjust the peak force set point and the peak force amplitude if needed, so make it as small as possible. And then you would scan over your surface and constantly monitor the scanning, and sometimes it's also good to use an offset just to avoid scanning over the contaminations like here. So if you're away from them, your tip stays cleaner longer. You should use the XY offsets again, find a good finding a good location. You should, for the calcite to get to the atomic structure, you should use 4 Hertz at 256 times 256 data points, or 512 times 512 data points. You would need 2 Hertz. And again, be patient. You might still wait some time to reduce the drift on the multimode system. And again, if it's not working, repeat the whole procedure from the beginning, including cleaning everything. Here's an image of peak force tapping on DNA. So this is also possible. If I remember correctly, this image was done on an icon system. Here, basically, this is how it's set up. Again, do everything, if possible, in air. Then you would wash also the mica and the fluid probe holder with a soap solution or IPA and a baby toothbrush, a soft toothbrush, and then rinse them again with DI or Milk water. Then you rinse mica and the probe holder with ethanol, then dry them with nitrogen, store them in a Petri dish. Then you use a Scotch tape to remove the top layer of the mica. Then some more details on the DNA side. So then you would filter nickel chloride solution and the buffer solutions with a syringe filter. You shouldn't filter the DNA solution because then you won't find your DNA. You apply 20 microliters of the nickel chloride solution on the mica and cover it with a Petri dish. You should incubate it for 5 to 10 minutes. After that, you add 10 microliters of the DNA solution and of the 20 microliters of the buffer. And then you would mix everything with a pipette just by sucking it in and out. You cover the sample of the Petri dish and let it incubate for 15 minutes before imaging. If needed, you could put a small piece of wet paper next to the inside the Petri dish next to the sample to reduce the evaporation effect here. Then you mount the sample on the AFM, and you should use tweezers and make sure that the tweezers do not touch the solution. Otherwise, again, you would come up with contamination. Mount the probe on the fluid holder as we did before. In this case, by the way, are pictures of the catalyst or resolve system. Align the laser in air again. This is the same as we did before. Here are the settings for it if people are interested. So this presentation will go out to you as well, so you have more details here. In the end, you will just reduce when you're on the surface, you would reduce the engaged set point to very small values. And then you reduce the set point after you have your to very low, so like 200 or 100 piconewtons. Scan size should be 1 to 2 microns, and you would scan with a low resolution in the beginning to find for DNA, and also don't forget to reduce the Z limit to 1 micrometer. And you would use here now the XY offset when you're looking for the DNA to move around. Wait, here we are. Once you find it, you can zoom into it at 500 nanometer scan size, reduce the set point even further to 100 piconewton, peak force amplitude to 10, lift height to 5, and then you can get a nice image of the DNA. You would see that the height will be about 2 nanometers. If you have a sharp tip, the width of the DNA will then show you at 4 to 6 nanometers, which means basically this is something which is available all the time, or that you always see in the XY AFM image. In X and Y, you also see a contribution of the tip to the width of the features. And then again, you would just reduce further your set point till you barely are on the surface, that you do not destroy anything. And then you wait a couple of frames for the system to stabilize. And then again, you would look for your DNA. But there still be DNA might floating around, and which means you would see a zigzag pattern. Finally, when you have your image, you would flatten the image and then would change that to get the best contrast here. again, this is for people who are going to measure DNA or similar features in the fluid cells. That's it from my side. Now I'm open for questions.
Thank you, Christian. So now we have our first question from Miguel. So the question is, would you describe some of the operations of PFT in fluid in Edge? I understand the alignment is the same as Icon.
Yes, the setup is in general the same. On the Edge system, you just there are some, or the differences is that you cannot get the QNM out of the Edge system, but you can get scanners. You can get a force image of your surface, and you can get an adhesion image. Overall, it is technically the same. The difference is, however, that you have to. The setup is slightly different. You need to. There's a small icon where you see on the Edge system where it says on the left-hand side it says auto gain and set point. And there's a small tool icon next to it where you can see then the force monitor and click on the auto config. So it should also work in liquid. Long story short, should work also on the Edge system in peak force in liquid should also work.
Okay, thanks, Christian. Next question is from Alexander. He asked, is it possible to measure in high damped liquids, for example, in liquids with the viscosity up to 300 times higher as of the water?
I would say in contact mode, yes. In peak force tapping, I never tried, but it's worth a try. If you would go for a SNLC, for instance, probe, you can either use it for contact in liquid or tapping in liquid or peak force in liquid. So this would be the ideal tip to test. I think it will be difficult because you have a very strong dampening effect there, and I'm not so sure about the absorption of the laser light. So this also depends. So our tips, by the way, are usually gold coated. So if you use something else like aluminum coating, which might not be good for cells, but also the aluminum might just dissolve in the liquid. So we use gold-coated cantilevers in this case. Contact should work as long as the light is enough light going back into the photodiode.
All right. Do we have, Alexander has another question. Is there are any disadvantages of scan assist probes? And can I basically measure with any probe in liquid? Or is there some restrictions to specific probes?
So from what I learned up to now is that scan assist works best if you have a coated cantilever. So you can use technically any coated cantilever, however, again, with the restriction, it has to be gold coated. Otherwise, the aluminum coating might just dissolve in liquid. So you can technically use any gold coated cantilever in liquid for scan assist in liquid. But I, again, for high resolution, use short, soft cantilevers, like the ones which were mentioned, SNLC, FastScan-C, or DNP-C probes. And or scan assist fluid as well, of course.
Okay, we got another question from Ladislav. Do I understand correctly that it is not possible to measure fluids which contain small particles around hundreds of so the fluid itself looks like milk?
Again, yes, it will be difficult because you cannot. The most important thing for the AFM is the reflection of a laser, and if you don't see the laser any longer, or it is just diffused, the light is just the laser light is just diffused. You cannot get a signal, then your system will not work. So, like milk wouldn't work, or if it's just too big, yes. Or if your particles are not fixed on the surface, then it will not work.
Okay. Another question from Mohammed. When engaging the cantilever, piezo goes to extended range, and it becomes difficult to engage cantilever at the position where piezo is at the middle. Any opinion to control this problem will be highly appreciated.
Okay, so assuming that it's in liquid, is the first question is can you see air bubbles, for instance, again the lamella formed in the V when the cantilever is basically, when you're engaged, is floating upwards, and then therefore system says, hey, I found a change of my set point, so I will start imaging now. So again, if you click on engage and your cantilevers, your motor either on the icon system or on the multi-mode system are not moving down, but you have an instant engage, you have a false engage, most probably two reasons. One is, again, a lamella, so you have an air bubble which floats up your cantilever, or which also happens from time to time if your cantilever already touched the surface and it's a silicon nitride cantilever, which is not breaking but bending, so it's bent upwards, and then you basically cannot get any stable scanning conditions, therefore replace the cantilever and dry everything and start all over.
We have another two questions from Ladislav. The first one, the fluid is just a mixture of cells which was distorted to see some polymers particles. How to fix the particles to the surface? Any general advice?
Since I'm a chemist, not a biologist, but if it's cells, if I understood correctly, there's a way for preparing the surface to make it more attractive to the surface for the cells than to go on the cantilever. So you can basically also passivate your tip or your cantilever. But please have a look into the literature. If you have an icon system, I think they are on the online help for biological samples. There is something, I can look something up and then maybe we can send this out to you if Jan gives me your email address, but I have to check myself. But it's basically, yeah, there are ways to optimize your surface to attract the particles you're interested in.
Okay, let's wait one more several seconds to see if there are any other questions. Okay, we're going to take 3 more questions. We have Alexander who asked that you mentioned some additional method to prevent the scanner of contamination with liquid. Can you explain it a bit closer?
Okay, so I was referring to non-liquid resistant scanners or scanners where you which are out of warranty, put it this way, where you have to be more careful. Usually the sealing should also last over the warranty, but again, there is no warranty then. What I usually use is a very thin layer of parafilm, which is this wax-like tape which you can stretch, and then you can overlay your scanner with it as well. Might add some noise to the measurement because it might also slightly vibrate or gives a bit more drift, but it also protects the scanner.
Thank you, Christian. And we have a question from Mohammed. I have cantilever holder with an O-ring already fixed with cantilever holder. Do we also need any other O-ring to seal the cell?
No, but now I have to think about. So most probably it's a multi-mode. I hope so. It's a multi-mode, and there is a there was a version where you really had O-rings, which were really like donuts, and they would snug good into the O form of the liquid cell. The later versions are a bit more softer and less and more flexible when you engage on the surface. So then you could basically also scan more easily over the surface in larger ranges. But you should at least also for cleaning remove the O-ring, clean it separately, and put it then back in. But you wouldn't need an additional O-ring. Or are you talking about the fluid cell for the icon system, which is used for electrochemistry? This would be my question back to him.
Okay, great. Thank you, Christian. And thanks again, everyone, to join our webinar today. Before we go, we would like to, in order to improve our webinar quality, I would like to invite you to do some, to answer some questions. So I'm going to open the poll. If you could just take 1 minute to answer. Okay, so we'll give another 10 minutes to 10 seconds to the first question. And then we'll move to the second one. Okay, the last question. Okay, that will be it. Thank you, everyone, and we'll send you an email with the recording and the presentation slides in maximum 3 days. So hope you enjoy the presentation, and we will meet the next time. Have a good day. Bye.
Thanks. Bye.